Hi guys. Okay, today I would like to discuss chapter 5 magnetic circuit. Okay, this is the part 1 of this chapter. Okay, the learning outcome for this topic is the first one is to explain the nature of magnetic field, explain the electromagnetism, explain the flux and flux density, discuss the magnetic circuit, and discuss the air gap fringings and laminated core. Okay, now the nature of the magnetic field. Okay, so magnetism is referred to the force that act between magnet and magnetic material. The region where the force exists is called magnetic field. Faraday concept, Faraday flux concept help us visualize this field. Magnetic field can be shown as line in space, flux line or line of force. Okay, this is the lines of the flux. Okay, this figure shows one permanent magnet which have the magnetic flux. Okay, so the symbol of magnetic flux is phi. Okay, this is the phi is the magnetic flux. The field is strongest at the pole. Okay, at the pole side, which is the south pole and the north pole. The direction flux line is from north to south externally. Okay, north to south, and flux line never cross. Okay, now the characteristic of line of magnetic flux. Okay, we have 5 characteristics. The first one is the direction of the line of magnetic flux at any point in the non-magnetic medium, such as air, is that of the north-seeking pole of the compass needle placed at that point. Okay, that is the direction of the line magnetic flux. Okay, each line of magnetic flux form a closed loop. Okay, line of magnetic flux never intersect. Flux line of opposite pole attract one another. Okay, they will attract one another, and flux line of same pole repel one another. Okay, then this is the characteristic. Okay, so ferromagnetic material. What is the ferromagnetic material? That is actually the magnetic material such as iron, nickel, cobalt and alloy. For non-magnetic material is, for example, plastic, wood and glass. Okay, for magnetic material, it will provide easy path for magnetic flux. Generally, there are two types of magnet. The first one is permanent magnet. Okay, and the second one is electromagnet. Okay, for permanent magnet, okay, the magnetic field is already there. Okay, but for electromagnet, okay, the basic principle for electromagnet, okay, the current, okay, must flow to the conductor, and it will create the magnetic field around the conductor. So, the current create magnetic field that concentrate about the conductor uniform along its length. Strength is directly proportional to I. So how to determine the direction of the current and the direction of the field? We can use the right hand rule. Okay, so the thumb, okay, shows the current, and the other finger shows the magnetic field. Or other versus vice versa, the current also can be the other fingers, and the thumb shows the magnetic field. Okay, if the conductor is wound into a coil, the field of each individual turns combined produce a resultant field. Okay, this is the field. Okay, the resultant field if the conductor is wound as a coil. Okay, next is if the coil is wound on a ferromagnetic core. Okay, this coil, okay, wound on a ferromatic core, okay, almost all flux is confined to the core, meaning the flux is flow through this core. Okay, although a small amount called stray or leakage flux pass through the surrounding air. Okay, now that the ferromatic is present, the core flux is no longer directly proportional to the current. Okay, now we see the flux and flux density. So magnetic flux is represented as the symbol of phi, and the unit is in Weber or WB. Magnetic flux density is the amount of flux per unit area perpendicular to the magnetic field. Its unit in Tesla or T. 1 Tesla equal to 1 Weber per square meter. Okay, so B or the flux density equal to phi flux over A area. Okay, and the unit in Tesla. Okay, we see example 1. Find the flux density in a magnetic field in which the flux in 0.1 meter squared area is 800 microweber. So to find the flux density, we use the formula B equal to phi over A. Okay, the phi is 800 microweber divided by area 0.1 meter squared, and we will get 8 millitesla. Okay, now you see the magnetic circuit. Okay, one of the characteristic of the line of magnetic flux is that each line form a closed loop. Okay, so this closed loop will make a magnetic circuit. Okay, and magnetic circuit are found in a motor, generator, transformer, computer, disk drive, and tape recorder, and so on. Okay, for air gap freezing and laminated core, okay, for magnetic circuit with air gap freezing occur, causing a decrease in flux density in the gap. Okay, for short gap, okay, freezing can be usually be neglected, but if the is quite big, so we cannot neglect the air gap. So laminated core has its effective cross-sectional area, then can be determined by using stacking factor. So what is stacking factor? Stacking factor is the effective area divided by the physical area. Okay, we see example 2. A laminated section of core has cross-sectional dimension of 0.03 meter by 0.05 meter, and stacking factor is 0.9. So find the effective area of the core, and if the flux is 1.4 milliweber, what is the flux density? Okay, so now we have to find first what is the effective area. So effective area is equal to stacking factor times the physical area. Then we will get this effective area. And for flux density is the phi divided by effective area. Then we will get this answer. Okay, this is exercise 1. Exercise 1, you have to answer this exercise to and submit to the MT assignment. Thank you.